Yeah, thank you for the introduction, and thank you very much to the organizers for the invitation to give this lecture. So this will be a presentation on Bayesian parameter estimation as applied to individual compact binary coalescences. So just to go over the topics that we'll cover, I'll start with some motivation for why we're interested in characterizing individual compact binary sources of gravitational waves. I'll go through an introduction to the statistical concepts that will be necessary throughout the rest of the talk. Then I'll talk about some of the properties of the LIGO noise that affect the likelihood that we use for analyzing the gravitational wave data, and then go into, presenting that likelihood. And then we'll talk about the astrophysical parameters that we are interested in constraining and the priors that we assume for those parameters, and then talk about Bayesian model selection, and then finally take a look at sampling methods for obtaining estimates of these parameters, and then time permitting, we can take a look at an example of how to use the real tools that the LIGO collaboration uses to analyze real LIGO data. So our goal with Bayesian parameter estimation is to go from strain that we see in the detectors and to turn it into some probability distribution for the parameters characterizing the source that the gravitational wave that we observed came from. So here you can see the strain in the Hanford detector from the gravitational wave event GW 150914, and hopefully after the lecture, you'll have a good understanding of how we take this strain and basically analyze it to obtain what are called these posterior probability distributions. And here you can see what's called a corner plot for the posterior probability of the two component masses of the black holes in GW 150914. So this lecture will be focused on how to measure the properties of individual compact binaries. So here you can see, again, this corner plot of the two component masses and then of the final mass and final spin of the first 11 compact binary detections, including the binary neutron star. But later today, in Salvo Vitale's talk, you will learn how to take basically the results that we obtained for the individual compact binaries and further analyze them to gain an understanding of the underlying population of sources. And that's called hierarchical inference. So you'll hear more about that later today. Okay, so to start off, basically the main theorem that we will use throughout the rest of the lecture is called Bayes' theorem, and many of you may be familiar with this already, but if not, just to review, what we are trying to obtain is the posterior, which is the probability of some parameters that we are trying to measure, in this case, for example, the masses and the spins of the black holes, given the fact that we've observed some data D and we're assuming some model H. And this is equal to the likelihood of having observed that data D given the binary parameters times the prior probability that we assume for those parameters. And then we're dividing by a quantity called the evidence. And this H model is hanging around on the right-hand side of all of these probability distributions because there's always a model assumed when we apply Bayes' theorem, even if it's not explicitly written. So we can break Bayes' theorem down into its components and take a look at each into a bit more detail. So the first thing, again, is the posterior. This is the probability of the parameters theta given the observed data D and our model H. So the likelihood is the probability of having observed that data, assuming some parameters theta and our model. And for the rest of the talk, I'll use this cursive L to denote the likelihood. And the other component in the numerator is the prior, which is just the initial probability of the parameters H under our, of the parameters theta under our model H. And this notation with the conditional bar just indicates that whatever's on the left depends on whatever's on the right.
Can you explain better the differences between all these things? Because I'm just, so the likelihood thing is the theory prediction or something like that, and the posterior is the observation. Can you just explain?
Yeah, so the posterior is what we're trying to obtain. If we go back here, this is a posterior. It's basically the probability of our source having some parameter. So it's the probability of, for example, GW150914 having a primary mass of 35. And in order to get this, we basically churn through the formalism of Bayes' theorem, and I'll spend a lot more detail talking about each of these pieces, but this is just kind of a big picture overview. So for example, for the prior, this is like what we think the parameters might be before we've even looked at our data. So if we go with the example of the masses, we know that LIGO is only sensitive to the mergers of stellar mass binary black holes. So our prior for our mass parameters might be between 5 and 100 solar masses, because we know we're not interested in supermassive black holes. So we don't let our prior go up to tens of thousands of solar masses. And the likelihood will go through and explain how we arrive at the form of the likelihood, which depends on the properties of LIGO data in great detail.
So I think my question is maybe how much are we biased? We're giving a number. Say this event can happen once in a 20 billion giga years, but at a false rate. But how much is this biased by what we input in the system?
Right. So Bayes' theorem is model dependent. So your result is only going to be as good as your model. If your data it contains, for example, a merger of, two protostars or something else whose signal is not determined by the assumption that we are looking for binary black holes, then whatever parameters you estimate are going to be biased because your model is not relevant. But we think we do a good job in choosing our models, and I will get to that also later in the talk.
So is there a way of testing this?
Yes, and I will also get to that. That's the model selection part of the talk. So you can analyze the same data with different models and see which one fits the data best, and that gives you a way to quantify statistically whether your model is good or not. Okay, so just to continue with some of the statistical background, all probability distributions need to be normalized, and what that just means is if you take your probability for some parameter called mu and integrate it over the allowed parameter space of mu, that should integrate to 1. And this is achieved by a process called marginalization. In the case of the likelihood, this is where you just integrate certain parameters out of the distribution. So for example, if our likelihood depends on two parameters, theta and mu, but we're not interested in theta, that's just like a nuisance parameter that we don't care about, we can take our likelihood, multiply it by our prior on theta, and integrate out over theta, and what we're left with is just the likelihood that depends on mu alone. And so I mentioned earlier that the normalization factor for the posterior is called the evidence, and this is just the likelihood marginalized over all the parameters. So again, if we have our likelihood, which depends on some vector of parameters, this time theta in bold, we can multiply that by our prior on those parameters, which is going to be multidimensional, and integrate out over all the parameters, and what we'll end up with is this probability of D given our model H, which I'll denote with this cursive Z throughout the rest of the talk. And again, the subscript H is there because there's always a model implied when you calculate the evidence. It might be that there's a binary black hole in your data. It might be that the data that you're looking at comes from a gravitational wave detector. So there are many underlying assumptions that you make that go into your model. And sometimes the distribution of one parameter can depend on another parameter. So one example is when we look at compact binary mergers, the secondary mass in the binary is defined to always be less than the primary mass. So if we know that the primary mass is 6, then the prior on our secondary mass can be no higher than 6. And so again, we denote this through this conditional bar. So the joint probability of both theta and mu, for example, is equal to the probability of theta given mu times the probability of mu, which might be independent. And so in this case, the marginalization process is pretty much the same, except your prior on the parameters theta also depends on mu, and when you integrate this out, your mu dependence is still present on the left-hand side there. Okay, so that's kind of the basic big picture overview of Bayes' theorem and the statistical tools that we'll need. And now we can go into deriving the likelihood that we use specifically for gravitational wave data analysis. And so in order to do this, we need to keep in mind the properties of the LIGO noise. So I know that you've had lectures all about, the LIGO instrument, how it's calibrated, what are some of the instrumental artifacts that can cause features in the noise that are not consistent with, the statistical expectation. So we'll just review kind of what are the statistical properties of the noise under the assumption that it's well behaved. So typically we assume that the noise, which here we're looking at the frequency domain representation of some data d, so this tilde denotes the Fourier transform of the strain, which is in the time domain. So the frequency domain strain d is equal to some underlying noise due to the basic performance of the detector plus some astrophysical contribution. And for us, we're particularly interested in compact binary mergers, but this can be whatever you want it to be. So we typically assume that the LIGO noise is stationary and Gaussian, and this allows us to characterize it by the power spectral density, or the PSD, and the PSD will be denoted with this Sn of f throughout the rest of the talk. And the way that this is calculated typically is you take the complex conjugate of the Fourier transform of the noise and multiply it with itself, and take the expectation value of this quantity, and what you get is the PSD, and multiplied by some normalization constants. So because the PSD has units of 1 on hertz, or time, and the FFT of the dimensionless strain also has units of time, we need to multiply by this factor of the segment duration. So this is just the length of the data that you've taken in seconds, and then divided by 2. So this is how we obtain our PSD. And so for well-behaved noise in the absence of a signal, the real and the imaginary parts of the frequency domain strain will each follow a unit Gaussian distribution about the square root of the PSD. And this is just called the amplitude spectral density, or ASD. And so in the time domain, the strain is real, but when you take the Fourier transform, it becomes complex. So here you can see a visualization of this. In blue is the real part of the data, and in orange is the square root of the PSD. And if in each of the frequency bins that are plotted here, I take the value of the data and divide it by the value of the ASD in that bin, and then I make a histogram, what I get is the blue data here, and I can compare that to a unit normal, which is shown in black. So this is what it means for LIGO data to be Gaussian. Basically, the real and the imaginary parts of the frequency domain data follow Gaussian in the ASD.
Can you explain what the right graph is again?
Yeah, so here what I've done is I've just taken, for each of the frequencies on the left graph, I've taken the value of the data in blue in that bin, divided it by the value of the ASD in that bin, and then I have that what's called that whitened data for each of the frequencies, and then I just histogram those values. And that's what's shown in the blue data here. And this is just to show that the whitened data, what you get by dividing the blue by the orange, is Gaussian. Okay, so as we said, the PSD is a key component for characterizing the LIGO data, and it will be a key component for the likelihood. So we need to calculate this somehow. There are typically two methods that are used. The first method is called the off-source method, or the periodogram method, or more commonly, Welch's method. And how this works is you take a long stretch of data, either before or after the segment that you want to analyze that you think has a signal. And the reason that you always exclude the segment with a signal is because you know that there's excess non-Gaussian power in that particular segment. And so if you're just trying to estimate the baseline noise properties of the detector, including that in your estimate will lead to a bias. So you take this long stretch of data, it's typically 32 times the length of the segment that you want to analyze. And you take that and you split it into short segments. And for each of those short segments, you window the data in each of the short segments. And the reason why we need to apply a window is because LIGO data is not periodic. So if we take our short segments and take an FFT of that directly without applying a window, there are discontinuities at the edges, and that introduces an artifact called spectral leakage. And what that looks like is it introduces a 1 on F behavior, so the PSD will just look like a power law, and it won't be a good estimate of the LIGO noise. And so in order to mitigate that spectral leakage, we just apply a window to each of the segments so that the strain in that segment goes and ends from 0 on both sides to make it periodic. So we take our windowed data and we calculate what's called the periodogram for each of those short segments, and that's just take the window, Fourier transform it, and multiply it by its complex conjugate. So this is this periodogram. And then after we have the periodograms from each of the individual segments, we take the median, and that gives us the PSD. And so the reason that we use the median rather than the mean for gravitational wave data is because the median is more resilient against outliers. So for example, if you did have a glitch in one of the segments that you're using to compute the PSD, that translates into excess power, and so that would introduce a bias in your estimate of the PSD, and the mean would be more susceptible to changing based on that outlier with the glitch, but the median is generally more robust. And you can see here two different PSDs that were calculated with two different durations of data. Again, so this is just the PSD as a function of frequency. In blue, it's calculated using a 64-second stretch of data, and in orange, it's calculated using a stretch of data that's 512 seconds long. And so one thing that you can see here basically is the longer the stretch of data that you use to calculate the PSD, the less noisy is your estimate. So as you add more data, your PSD converges to some underlying value. Basically what this means is that in order to get a good estimate of the PSD using the Welch's method, even though it's very computationally inexpensive because you're just doing a bunch of Fourier transforms, it's more likely that some segment of the data that you're using actually won't be Gaussian or stationary. So there's some chance that you'll be breaking this underlying assumption and you might get a biased estimate of the PSD. And so one way to avoid that is to use what's called the on-source method. And so here, the PSD is modeled as a sum of a broadband spline, which is shown here in red. Again, this is just the PSD as a function of frequency. And for the lines that you get in the PSD, those are modeled as Lorentzians. So in your previous lecture, I'm sure you heard all about, why we have these lines in the LIGO data, how they come from calibration and the violin modes, but we need to model them. And so in this baseline algorithm that was developed in this paper by Littenberg and Cornish in 2014, they model the broadband behavior with a spline and the narrowband behavior with Lorentzians. And so then you take the segment that you want to analyze and only data from that segment alone, and you infer the parameters of the spline and the Lorentzians for that segment. And you can simultaneously model and subtract any sort of excess power from non-Gaussianity. So if you have a signal or a glitch, you can just get rid of that, model it out, and so your underlying estimate of the PSD won't be biased. And again, so the advantage here is that it requires a lot less data, and if that data does happen to be non-Gaussian or non-stationary, you can model it out. The disadvantage, though, is that this is much more computationally expensive because you actually have to infer the parameters of the PSD instead of just calculating it by taking a series of Fourier transforms and averaging over that. Okay, so we saw how the data in the absence of a signal is Gaussian. So what that should mean is that if your data does have a signal, if you subtract it out, the residual, which is just the difference between the data and the signal template, that residual should also be Gaussian. So here we can write the probability of having observed the real part of the data given some binary parameters. It's just a Gaussian. So the usual expression for a Gaussian, we have one on the square root of 2 pi sigma squared, and this sigma may be frequency dependent. We'll see later that it is. And then this is just multiplied by e raised to the minus the residual squared divided by 2 times sigma squared. So again, this is just the same statement of the property of Gaussianity of the data, except in this case, we are correcting for the fact that the data might have a signal in it, which would make it non-Gaussian. If you subtract that signal out, the residual is Gaussian in each of the real and the imaginary parts. So what is that sigma factor that we use in the Gaussian on the previous slide? So it's basically just the PSD with, again, some normalization factors. So this value of sigma is going to be frequency dependent since the PSD varies as a function of frequency. And then we can get the total likelihood of having observed our frequency domain data D under the assumption of some binary parameters theta by multiplying the individual likelihoods of the real and the imaginary parts. So this is a common expression that we'll come to in subsequent slides as well. Basically, if you have independent likelihoods for two independent sets of data, in this case the real and the imaginary parts are independent, you can get the joint likelihood of both of those parts by multiplying the individual likelihoods together. Okay. And so if we want to see then what the final form of our gravitational wave likelihood is, we arrive at this expression for the Whittle likelihood, as it's called. So again, the likelihood of having observed the frequency domain data D in each frequency bin Fi, so the I is an index for the frequency bin, which depends on our binary parameters theta, is equal to 2 divided by the segment duration times pi times the PSD times e raised to the minus 2, and then this is just the residual, the data minus the waveform squared divided by the duration times the PSD. And this is the likelihood in each individual frequency bin. However, we have a whole range of frequencies that we are interested in analyzing. So again, the likelihood of observing the data in all the frequency bins is just the products of the likelihoods in the individual frequency bins. And again, we can apply this product of likelihoods one more time. And in many cases now we have a network of gravitational wave detectors that are each taking independent sets of data for the same stretch of time. And so if you want to combine the data from multiple interferometers, the likelihood of that data from that whole network is just the product of the likelihoods of the individual interferometers. And in this case, the data will change for each interferometer, and so will the PSD, because maybe they're operating with different sensitivities. Okay, so this is basically the likelihood that we use to analyze gravitational wave data and look for compact binaries and try to measure the parameters of the signal. But we can simplify this a little and define some interesting signal-to-noise ratios that will be useful down the line. And so in order to do this, we define what's called the noise-weighted inner product. And this is denoted with this bracket notation. So A inner B is defined as 4 divided by the duration of the segment being analyzed times a sum over frequencies, whoops, this should be an I, of the real part of the Fourier transform of A complex conjugated multiplied by the Fourier transform of B divided by the PSD. And so this is a sum over frequencies of basically this noise-weighted product of the two quantities that we are taking in this inner product. And as I said, this is just useful for simplifying the likelihood and defining the signal-to-noise ratios that we typically use to characterize how loud a particular signal is. So we can use that noise-weighted inner product to rearrange our log likelihood. So if we take the log of the likelihood that we saw previously, this is just the sum over frequencies of the log of the individual frequency likelihoods. And if we write this out, it looks like this. So this first term is just the normalization constant out front. It's the sum of the log of 2 over the duration times pi times the PSD in each frequency bin. And then we have minus the sum, again, over frequencies of 2 times the residual absolute value squared divided by the duration times the PSD. And so if we look closely at this term and compare it to the noise-weighted inner product, we can see that it is easy to rewrite in terms of the noise-weighted inner product. So if we drop this term, because it's just a normalization constant, it doesn't change as you vary the binary parameters theta, you can see that the log likelihood of the data is proportional to minus 1/2 times the noise-weighted inner product of the residual with itself. So we've taken this full form of the likelihood that we had here and rewritten it basically in terms of a simple inner product. Okay, and so now we can expand that further and define some signal-to-noise ratios. So if we expand the expression on the previous slide, we get 3 separate noise-weighted inner products. The first is the inner product of the data with itself. The second is the inner product of the data with the waveform or the signal model. And the third is the inner product of the signal with itself. So this third term is defined as the optimal signal-to-noise ratio squared. And this is basically if you get a signal with these parameters theta and you had absolutely no noise in the detector, this is how loud you would measure it to be. This is why it's optimal, because under this assumption, you're operating in an ideal detector with no noise. In reality, our detector does have noise, and so that is encapsulated in the match filter signal-to-noise ratio, which utilizes this second inner product here. So the match filter signal-to-noise ratio is the inner product of the data with the signal divided by the optimal signal-to-noise ratio. And so this quantity is a Gaussian about the optimal signal-to-noise ratio. So because of the noise, in some cases, you might end up with a signal that you think is louder than it really would be in the absence of noise, just because of the particular noise fluctuation. And in some cases, it might end up being softer. So these, again, are just useful ways to quantify how loud the signal is in the detectors. Okay, and then we need one more piece here. So far there's been an implicit hypothesis in the likelihood that we've written down, and that is that there actually is a signal in the data. So we need something for the H. If there actually is no signal, then the likelihood just simplifies. You set H to 0, and you end up with this expression, which I will denote with the empty set. So this is our noise likelihood. It's just the same normalization constant out front times e raised to the minus 2, the data absolute value squared divided by the signal duration times the PSD. And so we can rewrite this in the same way as we did with the signal likelihood as minus 1/2 times the inner product of the data with itself. And you can see that this term actually appears here as well. So our signal likelihood is proportional to our noise likelihood plus these different combinations of the optimal and match filter SNRs. So that's just a convenient way of writing the likelihood down. Okay, so now that we've looked at the properties of the LIGO data and translated that into a likelihood, we can spend some time investigating what the signal contribution actually is, what we've been calling H tilde of theta and F. So in our particular case, we are interested in looking at compact binary coalescences. So here, H of F is a waveform that depends on 17 parameters, well, up to 17 parameters. So these can be broadly divided into two categories. There are the intrinsic parameters, which consist of the masses of the two compact objects as well as their spins. So the spins are actually a three-dimensional vector for each compact object, so those represent a total of 6 parameters. And then if we have neutron stars in our binary, we also can take into account the tidal deformability, and that's just how soft the neutron star is, and it depends on the equation of state. And that's something that can be inferred from the gravitational wave data. And so here you can see a schematic of what a setup of a binary merger might look like. So we have our two black holes. Typically, M1 is ascribed to the more massive black hole and M2 to the least massive black hole. And then for our spin parameters, we can characterize them with a magnitude, chi, and a tilt. So here you can see the orbital angular momentum is straight along the z direction, but the spins of the individual components might be misaligned to the orbital angular momentum. And in this case, we have this parameter theta 1 and theta 2, which determines the tilt of the spins relative to the orbital angular momentum. And then we also have the extrinsic parameters, which determine basically just the relative orientation and position of the source relative to the observer. So we have the sky location, which is typically parameterized in terms of the right ascension and the declination. We have the distance to the source, the inclination angle, which is just the angle between the source and the line of sight of the observer. And we also have the phase and the time at the coalescence. So just some reference phase and time to know basically at what point we observe the merger. And so one way that we can parameterize the inclination is with this angle iota, and that, as you can see, is the angle between the orbital angular momentum and the line of sight of the observer, which is denoted with n hat. And one thing that I haven't written down here is also the eccentricity of the binary. So in LIGO, we assume that the sources are quasi-circular and they basically have negligible eccentricity when they merge and they're observed, but it's possible that some systems might have residual eccentricity. It's just that the development of the waveforms, including eccentricity, is much farther behind than for the quasi-circular sources. And again, it's possible that this astrophysical contribution comes from a different type of signal. If you have something and you're not sure that it's a compact binary, you can model it with a sum of sine Gaussian wavelets. There are also waveforms for predictions for the signal from supernovae. So this can be anything you want it to be. It's just that for now we're interested in compact binaries. Okay, so how do we actually measure these parameters from the waveform? So again, if I write out the vector of binary parameters theta that we've seen so far, this includes the two masses, the 6-dimensional spins, potentially the tidal deformabilities, which are called lambda if there's a neutron star in the binary, and then the inclination, the distance, the right ascension, the declination, the polarization angle, which basically just determines the relative orientation of the source with respect to the detector, and then the reference phase and time. So this polarization angle enters because gravitational waves are emitted along two orthogonal polarizations. They're called the plus and the cross modes, and this is in general relativity. If you have an alternative theory of gravity, there are up to 6 polarizations, but for now we're going to assume general relativity is correct. And so here you can see an animation of how these two polarizations affect a ring of test particles, and unsurprisingly, the plus mode will deform the ring of particles into a plus shape, and the cross mode will deform it into a cross. So we can break the waveform down into the two polarizations. And so for the plus polarization, the waveform is equal to 1/2 times the amplitude of the gravitational wave signal times 1 plus the cosine squared of the inclination times the cosine of the gravitational wave phase. And this is not the same phase that is up here. This is the overall phase of the gravitational radiation, which depends on the intrinsic parameters of the source, like the masses and the spins. And the amplitude also depends on those parameters and also the distance. And for our plus polarization, we have that it's equal to the amplitude times the cosine of the inclination times the sine of the gravitational wave phase. Okay, so the intrinsic parameters affect the waveform via the amplitude and the phase. And how about the extrinsic parameters? So they enter the final waveform that is observed via what's called the detector response. So the detector's sensitivity to the two different polarizations of gravitational waves depends on its orientation and geometry via what are called the antenna pattern functions. So these are these f plus and f cross functions that depend on the right ascension, the declination, and the polarization. And you can see what they look like here, the plus polarization and the cross polarization for the two LIGO detectors. So this depends on basically the opening angle between the arms. And basically what this tells you is how sensitive the detector is to gravitational waves of each polarization coming in different parts of the sky. So you can imagine for this cross polarization, if the gravitational wave comes basically right along the plane of the, like along the equator, then it won't be detected in the instrument at all. And that just basically tells you that if you got a cross polarized gravitational wave coming, straight down along one of the arms, the deformation and the stretching and squeezing of spacetime would be such that it would be missed by the interferometer. So then the final waveform that we observe in the detector is just the antenna pattern times the astrophysical contribution for each of the two polarizations, and then you sum both of the two polarizations. And these antenna patterns are calculated by contracting the polarization tensor with the detector tensor, and that's basically just constructed from the relative orientation of the arms. So again, it's basically just a purely geometric factor. Okay, so what are the parameters that we are actually trying to measure here in a bit more detail? As I mentioned earlier, we typically use primary to refer to the more massive black hole and secondary to the least massive black hole. And the best measured mass parameter with gravitational waves is called the chirp mass. So this is the leading order contribution from the masses of the source to the waveform, and that's why it's the easiest to measure. And it is this particular combination of the component masses, so m1 times m2 raised to the 3/5 divided by m1 plus m2 to the 1/5. And we can also look at what's called the symmetric mass ratio. So this is notated with eta, and this is just m1 times m2 divided by m1 plus m2 squared. And again, this is just the particular combination of masses that enters the waveform at leading order. So this is why it's convenient to work with this particular version of the mass ratio. But we can also work with the asymmetric mass ratio, which is defined as Q equals M2 divided by M1. And so in this case, Q is constrained to be between 0 and 1 because M2 is the less massive of the two. While in numerical relativity, sometimes this convention is different, and the relativists like to use Q greater than 1, so you would just take the reciprocal of this. But for parameter estimation, it's just more convenient to sample in a bounded parameter rather than one that has infinite prior support. So instead of letting Q go out to arbitrarily large values, it's just easier to bound it between 0 and 1. Okay, and so what actual astrophysics can we learn by measuring the mass parameters? So the masses are indicative of supernova physics. So for example, some theoretical models and also the observations of neutron stars and black holes in our galaxy via X-ray binaries show that there should be a lower mass gap between the most massive neutron stars and the least massive black holes formed directly in supernovae. So we don't know what the maximum mass of a neutron star should be. Again, this varies based on the equation of state that you assume, but it's around 2.2 solar masses, and this is also consistent with observations. And then, the least massive black holes that have been observed in the galaxy are around 5 solar masses. So there should be this region between around 2.2 and 5 where we don't see any compact objects. And this is already being challenged. So one particular interesting individual event where the masses can tell us something about supernova physics is GW 1908-14, which was observed in the last observing run. And so we know the primary in this case is a black hole, but the secondary has a mass of 2.6 solar masses. So this lies in this putative lower mass gap, and we don't know if it's the most massive neutron star ever observed or the least massive black hole. But it is the first time that we've observed something to live in this mass gap. So that can tell us about how such compact objects form. And then on the other side, we have an upper mass gap, which is predicted because theoretical models say that basically stars with masses in the range of 140 to 260 times the mass of the sun should not collapse to a black hole. Instead, the whole star basically gets blown apart due to instability caused by pair production during the supernova, and so there's no remnant left, and so we shouldn't detect black holes that are more massive than about 50 solar masses. And this is also already being challenged because we detected GW 1905-21, where at least the primary is living in this upper mass gap. So this is what we can learn with the masses. And how do we actually extract this information from the waveform? It's pretty simple, at least to leading order. The bigger the mass, the bigger the amplitude of the waveform. And you can see here that the amplitude is proportional to the chirp mass to the 5.6, the frequency to the minus 7.6, and then inversely proportional to the distance. And so there are 3 regimes here that we can measure and probe with gravitational waves with LIGO. The early regime is called the in-spiral. This is when the 2 sources are decently far apart and they're just in-spiraling and approaching each other. And then there's the merger part, which we usually take to be the peak of the gravitational wave strain. And then there's the ring down. So the final black hole that forms after the merger will be slightly perturbed, and it will ring down like a bell, emitting gravitational radiation primarily at one frequency via a damped sinusoid, but then also in a series of overtones. And so the final mass is measured from the ring down part of the signal that we see, and the chirp mass is measured very well from the in-spiral. And now we can also take a look at the spin parameters. So as I mentioned previously, it's possible that the component spins will not be perfectly aligned with the orbital angular momentum, and this causes a phenomenon called precession, where both the orbital plane will precess and also the component spins will precess around the total angular momentum. So again, here, in this case, I'm denoting the total angular momentum with J. And so we talked about the magnitudes, the chi1 and chi2 of each of the spins of the two objects and the tilts of the spins relative to the orbital angular momentum, but we need two more angles in our spherical representation of the spins to get to 6 degrees of freedom. The first is phi 1, 2, which is just the azimuthal angle between the projections of the two spins onto the orbital plane. And then the second angle is phi JL, which is the azimuthal phase of the orbital angular momentum L in its precession cone around the total angular momentum J. And we can define one other inclination parameter here as well, called theta Jn. So previously I introduced iota as the angle between L and N, but if the system is precessing, then L wobbles, and so iota is not going to be constant, whereas theta Jn is the angle between the total angular momentum and the observer line of sight. And so the total angular momentum is fixed, and so this will be constant throughout the evolution of the system. And the reason that we use this spherical representation of the spins instead of, for example, just the 6-dimensional XYZ Cartesian components is because it's easier to apply an astrophysically motivated prior on the angles and magnitudes than it is on the Cartesian components. And so I'll talk about the priors in a few slides. Okay, so in addition to the 6-dimensional spins, there are two other important spin parameters that we measure with gravitational waves. The first is chi-effective, and this is the best measured spin parameter with gravitational waves in the same way that Chirp mass is for mass. And this is, again, just because it enters at leading post-Newtonian order in the waveform. So chi-effective is the mass-weighted spin aligned with the orbital angular momentum. So it's defined as chi1 times cos of tilt 1 plus q, the mass ratio, times chi2 times the cos of tilt 2 divided by 1 plus q. So again, you're just taking the spins and projecting them along the orbital angular momentum. And we can define a similar quantity to encapsulate the effects of precession. So this is chi-p, the effect of precessing spin. And this is now just the mass-weighted spin projection onto the orbital plane. And it is defined with this maximum. So it's the maximum of chi1 times psi1, sine of tilt 1, or 4q plus 3 divided by 4 plus 3q times q times chi2 times sine of tilt 2. So again, this just tells you how much precession is occurring in the particular system that you are looking at. And the reason that we want to measure the spin parameters is, again, they can tell us about the interesting astrophysical processes that lead to the formation of these binaries. So typically, there are two main formation channels that we think lead to the double compact objects that are then eventually observed with LIGO. The first is what's called the isolated binary evolution formation channel. So you start out with two massive stars in a binary, and they go through their whole life cycles together, and they eventually die and become a compact binary. And so in this case, because they evolve together, the spins of the compact objects are expected to be aligned with the orbital angular momentum. The other formation channel is the dynamical formation channel. So here, the compact binaries are assembled dynamically in dense environments. And so in this case, if you create a binary just by like a random gravitational encounter between two objects that are, say, in like a globular cluster or a nuclear star cluster, then you would expect the spins of those two compact objects to be isotropically distributed in direction. And so if, for example, you measure a binary that has a significant amount of precession because the tilts are misaligned, then that can be an indication that it formed dynamically. The azimuthal angles also actually carry information about the binaries history as well. So the azimuthal angle phi 1,2 can be indicative of the efficiency of tidal interactions during the stellar evolution. So if there are efficient tides while the two stars are evolving in the isolated evolution channel, basically the orbital angular momentum and the two spin vectors can become locked in a 2D plane and jointly process about the total angular momentum J at the same frequency. And this is called a spin orbit resonance. And so in this case, that means that phi 1,2 would preferentially be 0 or 180 degrees because they're locked in a 2D plane. So if you would observe a system that has a phi 1,2 of one of those values, that might tell you that it's locked in one of these spin orbit resonances. And again, that would tell you how it formed. And finally, all of the spin angles, including also now the second azimuthal angle phi JL, are critical for determining the kick of the remnant object. So gravitational waves radiate away angular momentum, and for angular momentum to be conserved at the end of the merger, the remnant object is basically imparted with a kick, so a velocity along some direction with some magnitude. And the magnitude of the kick can determine the retention fraction of the remnant compact object in its environment. So for example, if it did occur dynamically in a globular cluster and you had a kick that was greater than the escape velocity of the cluster, then that black hole would be ejected and it would not be able to stick around in the cluster and interact with other black holes and eventually maybe merge again. And so that determines the fraction of what's called second generation mergers, where one of the compact objects remaining in the binary is the remnant of a previous merger. And kick velocities are typically around a few hundred kilometers per second. They depend, again, very sensitively on the spins and also on the mass ratio. So if you have more unequal masses or just aligned spins, that will give you a smaller kick. But in some what are called super kick configurations, you can get velocities up to like 5,000 kilometers per second. Okay, and the spin enters the waveform through two easily distinguishable effects. The first is what's called the orbital hang-up effect. So if you have a more positive aligned spin, it just takes longer for a system with the same masses to merge relative to a non-spinning system. You can see that here. In blue is a non-spinning system, and in red is a system with a high aligned spin. And the waveform is just longer, so the presence of the spin delays the merger. And then when you have precession, this introduces amplitude modulations in the waveform. So in blue here, you can see an aligned spin waveform, and basically the amplitude is monotonically increasing up until the point of the merger. While if you have precessing spin, you can see that the amplitude actually decreases here. And so you get these lower frequency wobbles due to the precession in the waveform. Right, and so now we can talk about the priors that we apply to these parameters when we try to measure them using Bayesian inference. So we usually choose the priors to be uniform in some parametrization of the mass. And in this case, usually what we assume for individual compact binaries is we want to take the priors to be uninformative. So later in Salvo Vitelli's talk, he'll probably tell you how you can use the previous observations of the population of binaries to update your priors to include astrophysical information. But for our case, we're just going to assume we want our priors to be uninformative so we don't miss something unknown in the parameter space. And so the easiest choice is just a sample in the chirp mass and the mass ratio, again, because the chirp mass is the best measured parameter. And so that parameter will converge the quickest to its true value, and that will help the sampling. And again, we have to enforce in the prior that the primary mass is greater than the secondary mass. And now here, for the spin degrees of freedom, we typically assume that the spin magnitudes are uniform between 0 and 1, which is the maximal spin for a Kerr black hole. and that the angles are isotropic on the sphere. So the tilt angles, and that's why we choose to use that parametrization. And then the azimuthal angles are just also assumed to be uniform. For the extrinsic parameters, we assume that the sources are distributed isotropically on the sky for right ascension and declination. And then for the distance, there are a couple choices. So one is assuming a uniform in luminosity volume prior, so proportional to the luminosity distance squared. And this is just because with gravitational waves, what you measure is the luminosity distance directly. So for nearby sources, here you can see the shape of the prior probability distribution as a function of distance in megaparsecs. So for small distances, up to 500 or so megaparsecs, the choice of distance prior doesn't matter that much because the cosmological effects are small. So here are three different priors. In orange is this uniform in luminosity volume prior. In blue is a prior that is uniform in co-moving volume and source frame time. And then in green is a prior that's just uniform in co-moving volume. And so again, at low distances, they're pretty similar, but as you go out to high distances, pushing the reach of the current generation of gravitational wave detectors, here we're at 7 gigaparsecs, they do begin to differ substantially. And in particular, this uniform in luminosity volume prior puts a lot of prior weight at very far distances. And so you want to choose the prior so that basically you're not spending a lot of time exploring these very, very distant parts of the parameter space if you know your source won't necessarily be there. Okay, and then basically the last component that we need before we can plug along and run our parameter estimation is some sort of model for the waveform. And this is just because, as you all have been learning in the previous lectures, it is very expensive to run numerical relativity simulations all across the parameter space of interest. So you need some sort of cheap approximative method to get the astrophysical contribution H. And so Patricia Schmidt will give a talk all about this tomorrow, so I will only just very briefly mention this. There are a few different methods for obtaining these approximative solutions. The first is just the post-Newtonian in-spiral-only waveforms. So in the regime far from merger, this is a decent approximation. Then you have in-spiral merger ring-down phenomenological waveform models that are tuned to numerical relativity, and these are decently accurate across the 3 stages of the merger. And then there are other methods for approximating the solution, including the effective one-body or self-force methods. And then more recently, there have also been numerical relativity surrogate models developed that basically interpolate between different numerical relativity waveforms that already exist. So the choice of which waveform model or which approximation here to use really depends on the type of system that you're analyzing, because different models will include different physics. So not all models will include the effect of tides. If you know there might be a binary neutron star or a neutron star black hole merger in your data, then you want to make sure that you use a waveform model that allows for the possibility of tides. If you think that your component spins might be misaligned, then you need to choose a waveform model that includes precession. And again, another thing is higher order modes. So if you decompose the signal into spin-weighted spherical harmonics, the dominant emission mode for the gravitational wave radiation will be the 2-2 mode. But particularly for asymmetric mass mergers like GW190412 that was observed by LIGO in 03, the emission in the higher order spherical harmonic modes will also contribute significantly. So you don't want to choose a waveform that doesn't include this contribution, and then you might get a biased estimate of the rest of the parameter. So this kind of ties into the question in the beginning. Your parameter inference is only as good as your model. So if you choose a model that does not adequately cover the physics that is included in your source, then you will get a biased estimate. And that segues nicely into Bayesian model selection, which basically allows us to quantify how good a certain model is at describing our data and compare it to a different model. So as a simple example, we can consider the case of whether there is a signal or pure noise in the data that we're analyzing. So in order to calculate this, we need one other piece, which is the noise evidence. And again, our evidence is just our likelihood integrated over our prior. So we take our noise likelihood, which was again denoted by that empty set and has h set to 0, and we integrate it over the binary parameters. And because the noise likelihood does not depend on the binary parameters, we can pull it out. And if our prior is properly normalized, then this part of the integral just goes to 1. And so what we're left with is the noise evidence is equal to the noise likelihood. So then how do we quantify our confidence in the fact that there is a signal in the data? This is done through what's called a Bayes factor, and this is just a ratio of the evidences. So we previously saw how to calculate the signal evidence. You take your signal likelihood and integrate it over your allowed prior parameter space. And we just saw on the last slide how to calculate the noise likelihood. So our Bayes factor between signal and noise tells you basically how confident we are that there is a signal in the data, and it's just the ratio of the two evidences. We can also use what's called an odds ratio. So here, this is the Bayes factor weighted by the prior odds. And so here's your Bayes factor, and you're multiplying it by your prior probability of signal divided by your prior probability of noise. So usually for the signal to noise question, we assume there are equal odds, but this might not always be the case. So for example, if you wanted to compare a GR waveform with a non-GR waveform, you might ascribe more weight a priori to GR just because we think it's right and it's withstood many tests. Another example is if you wanted to look at the probability of it being a quasi-circular merger versus a head-on collision. There are geometric factors that would affect your prior odds there. So it's not always the case that the prior odds is 1, but in many cases it's fine to just look at the Bayes factor. And so we can look at another example here related to the waveform question, which is whether the system has aligned or precessing spins. And so in the previous example of the signal to noise case, what we varied to cause the evidence to change was actually the likelihood. So in one case it had a signal and in the other case it didn't. But if we want to look at the aligned versus precessing spin scenario, the likelihood is the same. It's just the priors change. So for aligned spins, the prior on all the spin angles, the tilts and the azimuthal angles, is just going to be a delta function at 0. And so here, the prior parameter space that we are integrating over changes between the aligned model and the precessing model. So the Bayes factor would just be the evidence calculated under one prior divided by the evidence calculated with the other. And how we quantify a strong statistical preference for one or the other is basically a Bayes factor of approximately greater than 3,000. So that would indicate a strong preference for one method over the other. Okay, and now we have all the pieces needed to perform parameter estimation, but how do we actually obtain this posterior on the parameters data that we've been talking about for the last hour? So again, this requires an integral because it needs to be normalized, and it requires that product of the likelihood and the prior. So you could do this on a really big grid with all 15 or 17 parameters that you're interested in, but this really isn't feasible in such a high dimensional space because the number of grid points that you need explodes. So instead, we typically use a stochastic sampler, and there are two main algorithms. The first is Markov chain Monte Carlo, or MCMC, and the second is nested sampling. And a stochastic sampler basically allows you to obtain samples from the posterior probability distribution directly. So instead of having a continuous representation for P of theta as a smooth function, you just get samples from theta directly. And so we can look at how these two work in brief. So for MCMC, the basic principle is that particles undergo a random walk through the parameter space, and you need one other piece in order for this to work. This is the proposal density function that basically tells the random walker where to jump to. And you can see a demonstration here of how this works. And so once you've made your jump based on your proposal density function, the probability that that new location that you've jumped to will be accepted is just the ratio of the product of the likelihood, the prior, and the proposal distribution at the old versus the new points. And so the key part for MCMC is determining a suitable proposal density function. And so this will determine the efficiency of your sampling and how long it takes and whether or not your resultant samples are biased or not. So a simple example is a Gaussian centered on the current location of the walker for each of the parameters. But you need to make sure that your proposal distribution maintains detailed balance, which means the probability of jumping between 2 points in parameter space is the same in both directions. Now for MCMC, the walkers, when they start off, take a while to forget where they came from. So the samples that you obtain at the start of the walk are going to be biased, and this is called the burn-in period. And so there are many different empirical ways to determine, how long this burn-in period is, but basically you just have to throw away all those points because it's a biased representation of the posterior, just because the walker had to start somewhere. And similarly, as it continues walking throughout the space, adjacent samples in the chain are also correlated. And so the chains need to be thinned by what's called the integrated autocorrelation time. And this is just the number of steps the walker has to take before it forgets where it came from. And so you want to choose your proposal so that you have a smaller autocorrelation time, because that way you don't need to thin your chains as frequently, and so the sampler can converge faster. Okay, and so the next algorithm for obtaining samples is called nested sampling, and how this works in broad strokes is that you sprinkle a set of live points over the prior space. So here is a figure showing 4 live points. And then you take the live point with the lowest likelihood and replace it with a new live point with from a part of the space that has a higher likelihood. And one of the downsides of MCMC is that while it gives you samples from the posterior, it doesn't calculate the evidence as a byproduct. So you would need to go through some additional computational steps to obtain the evidence if you're interested in model selection. While with nested sampling, the evidence just comes out of the algorithm. So here the evidence is the product of the likelihood at the discarded point and the difference in the prior volume between these iterations as you go through and replace the lowest likelihood point. And so this allows you to obtain samples from the prior and, from the posterior, and also calculate the evidence simultaneously. And this process of, replacing the lowest likelihood point basically continues until some preset termination criterion. So you would normally tell the sampler, I want you to keep going until the error estimate on my evidence is less than X. And so it just stops once it has a good enough estimate of the evidence. And I had a few more slides describing this in more detail, but I think for the sake of time, maybe I'll stop and save some time for questions, unless, I don't know, the organizer want to go over a bit, or we can just stop and go to questions, I guess.
Are there any questions so far? Yes, there are some questions in the audience.
Is there a downside to nested sampling? Is it slower than MCMC?
It can be. So basically, how you draw your live points from the prior space can be inefficient, particularly as you have done this process many, many times and you zone in on the highest probability part of the likelihood. It can be hard to find samples with hard to find new samples with higher likelihood, but there are clever ways to get the nested sampler to explore the prior space. It's also suboptimal for multimodal distributions in its most basic form, but again, there are modifications to it that allow you to sample multimodal distributions, just because you might have missed an island of probability out here if you're just zoning in on one, whereas with MCMC, if you've developed a smart proposal distribution, it should have you jumping between multiple different islands of probability.
Any other questions? You still have 7 minutes if you like to go on a little bit more.
Okay. Yeah, so we can look at nested sampling in more detail and show how that evidence is calculated. So the evidence is, again, just the expectation value of the likelihood, and this can be obtained by integrating over 1 minus the CDF of the likelihood. So this is just a lemma from statistics that you can get the expectation value of a quantity by integrating from 0 to infinity 1 minus the CDF of that quantity. So if we get the CDF of the likelihood, then the evidence basically reduces to a one-dimensional integral. And so the CDF of the likelihood is just the area enclosed in regions of the parameter space where the likelihood is less than some value L. So if we go back to the diagram here, if we wanted the CDF at L2, it would just be the area enclosed in this region outside the L2 isolikelihood contour. And so we can define a quantity called the prior volume, and this will denote with x of L, and this is just 1 minus this CDF. And so this is the area enclosed in regions that have a likelihood value higher than L. So it would be basically all of this region here for L2. And this prior volume is a monotonically increasing function between 0 and 1. So at the point of max probability, your prior volume is 0 because there are no points in the parameter space that have a higher likelihood. And at the point where your likelihood is 0, your prior volume is 1 if you've chosen a properly normalized prior, because you're just integrating the whole prior space. And so this tells us that this is a convenient parameter to use because it's monotonic and bounded. So this allows us to turn the evidence integral into a one-dimensional integral. So again, our evidence is just the integral between 0 and infinity of the prior volume of L, integrated over L because the likelihood can have any value between 0 and infinity. However, if we invert this x of L and calculate the likelihood at a specific value of the prior volume, then this becomes bounded, and it's just the integral of that inverse from 0 to 1. And so you can see this demonstrated here. So for example, for our 4 live points that we had, if the likelihood of the lowest likelihood live point is, for example, 0.004, then this tells you that 3/4 of the draws from the prior will have a likelihood greater than that 1 live point of 0.004. So this is how we are able to kind of build this one-dimensional integral for z as a function of the prior volume. Basically, you keep going, and at each iteration, you go towards higher parts of the likelihood until eventually you reach your termination criterion. So, once you've done this repetition of throwing out the lowest likelihood live point many, many times, eventually you've zoned in on the part where the prior volume is very close to 0. And so here you're close to the highest likelihood part of the surface. And once you basically do this one-dimensional integral, you can do it as a simple sum, pretty much. That will give you the value of the evidence. And so how we do this is with the Bayesian inference library. Typically, this is one of the parameter estimation packages that is used by LIGO. So it's designed to enable parameter estimation for compact binary coalescences and also more general problems. And it is very modular and hopefully easy to use with the thorough reading of the documentation. And this is because it's a wrapper to many different external samplers. So the samplers that we support are Dynasty, PyMultiNest, CPNest, MC, TempC, and a few others. And it can be used to analyze, real LIGO data or simulated signals, compact binaries, supernovae, sine Gaussians, whatever sort of astrophysical signal you want to consider. And so I don't have a lot of time, but I will just show you quickly. I can paste a link in the chat to a Jupyter Notebook tutorial from our Open Data Workshop course for getting familiar with Bilby. I don't know if that can be shared or I can send it around later, but just to show you a bit how this works in the last few minutes. Okay, I'm just gonna install the requisite packages. So this is a tutorial for how to run parameter estimation on GW150914. It goes through the process of downloading the data from the public servers and then setting up the likelihood and the priors and the various sampler settings to basically run the analysis with Bilby. Okay, and I'll just let this run in the background. So first we need to know the time of the event. This we just take from the GWASC website, the Gravitational-Wave Open Science Center. And so Bilby has these objects. Again, it's object-oriented and modular. So you can initialize these interferometer objects that have the geometric properties of the Hanford and Livingston detectors. We do that here, and then we need to grab our data. So we can use a package called GWPy, which interfaces with the Open Science Center to download the public data. And we're saying if this is the time of the event, we can query for a data segment that is 4 seconds long. Since it's a binary black hole, the data doesn't have to be too long. And we want our merger to occur in the middle of the segment. So this is this post-trigger duration. And so we query the server for the data that we want to analyze here. And it's downloading, and eventually we will plot the strain. And it won't look particularly meaningful because it's at a strange sampling frequency, but we will eventually look at it in the frequency domain. Okay, so now we add that data to our Bilby interferometer objects, H1 and L1. Now we need to download the data that we're going to use to calculate the prime spectral density. So again, as I said, a typical choice is just 32 times the duration of the segment you're analyzing. And we'll just do the same thing here. We're taking data from before the analysis segment and downloading it. And then again here, we're using a GWPy algorithm to calculate the PSD. This PSD alpha just sets the basically the aggressiveness of the window that we apply to that data when we use, in this case, the Welsh method for calculating the PSD. So it's downloading the data and it will do just exactly what we talked about. We'll split that small data into segments, apply a window determined by this PSD alpha, and then take the FFT and output that resultant PSD into our interferometer objects. Okay. So now we can plot our data and the PSD. This is the data that we downloaded. This is what it looks like. You can see this turnover at high frequencies. This is just an artifact of the basically the downsampling. So because we used a sampling frequency of 2048 hertz, the Nyquist frequency, or the max frequency included in the data, is just half that. But this is a binary black hole merger, so it merges at a few hundred hertz in the LIGO band. So we can safely just ignore this data because it won't have any relative or relevant information for our signal. So we replot it, and we've gotten rid of that artifact. Okay, and so now here is basically where we set up the prior and the likelihood now that we've obtained our data. So here, just for the sake of time, we'll sample only in the chirp mass, the mass ratio, and the phase and the time at coalescence. Again, chirp mass and mass ratio because those things are easier to measure. And we'll use what's called a Bilby prior dict object. So here we're using uniform distributions for these parameters. And everything else we're fixing to reasonable choices based on the more rigorous previous parameter estimation that has been conducted for this event. So we've initialized the prior, and now we need to create a likelihood. So Bilby already has that full Whittle likelihood that we showed previously included in the package, so we don't need to code that up from scratch. But we do need to feed it some information. So we tell it, the data is located in our two interferometers, and then we need to tell it what waveform to use. So we're going to use the IMR phenom PV2 waveform, which is one of those phenomenological waveform models that includes the effects of precession, but not higher order modes, which is okay because GW150914 is close to equal mass. And we'll say define the spins at a reference frequency of 100 hertz. And again, as we said, for processing systems, the spins change directions throughout the evolution of the binary. And so we need to measure them at some point in the evolution. And we're going to say measure them when the frequency of the gravitational wave emission is 100 hertz. So we define a waveform generator object that will allow us to generate the h of f quickly during the sampling. And then we finally set up our likelihood. So we tell it the priors, the waveform generator, where our data is. And then these marginalizations, I did not have time to talk about, but basically for certain parameters, you can analytically marginalize them out of the likelihood. And this just helps the sampling because you don't need to sample in those parameters, and it reduces the dimensionality of the space. And now we just set Bilby going. So we're telling Bilby to run sampler. It's using the dynasty sampler, and it will hopefully give us some posterior samples eventually. So I can let that run, and if there are any other questions, hopefully by the time this is finished, I can answer them simultaneously.
Any other questions? And the remote audience, anyone has questions? Oh, here in the person, Fabricio.
Yes, I have a question. I mean, it's maybe a naive question because it's maybe something I didn't understand exactly. But when you do Bayesian inference, you have, so as we said, it's something that is model dependent. So, I mean, my question is, how can you take into account, for example, new physics that you don't know? Like, I don't know, if you consider one signal, for example, one gravitational wave signal, and you consider like quasi-circular black hole coalescence or something like that. I mean, in this case, what you obtain for your base factor is dependent on the model that you choose. So how can you try to understand if there is something new, if there is, I mean, for example, you said that you use general relativity, but if you want to consider something different, what should you do? You should change the model and evaluate another base factor, or, I mean, I don't know if I...
Yeah, no, that's a good question. And you're exactly right. So there are ways to look for new physics, and we typically do this for LIGO signals. So as an example, the analysis that we've looked at assumes GR, as you said. You can introduce parameterized deviations from the typical GR waveform via extra bumps or features in the waveform. And you can fit for those extra parameters and include them in your model. And then you can compute a base factor between your waveform that allows for deviations from GR versus one that doesn't. So that's one way. Another way is to just use signed Gaussian wavelets. So instead of assuming, our signal comes from the merger of two black holes or neutron stars, you can say, I have no idea what it is. I'm just going to use the most generic model possible, which is just a bunch of signed Gaussians. And so that should be able to fit the signal, the shape of the signal well, but it won't really tell you anything about the astrophysical parameters because it's not like a physically motivated model. But for example, you can look at the residual between your standard analysis, assuming the standard waveform, and your signed Gaussian. So if you subtract your best fitting waveform from your data and you see that there's still power left, that means that some part of the signal, some new physics hasn't been accommodated by the model that you've assumed. Whereas if you use your signed Gaussian wavelets, it'll hopefully subtract out, all the power in the signal. And so you should have basically pure noise left. And so if that's one way, it's called a residual test. And that was performed for GW 15914. It's performed for many of these like exceptional events that we think might be a candidate for new physics. But yeah, as you said, you do need some sort of model to use that can tell you specifically the hypothesis that you're trying to test. So if you had eccentric waveforms, and there are some, but they're very computationally expensive to evaluate, so it just takes a really long time to run parameter estimation with those. If you had eccentric waveforms, you could compute a Bayes factor between eccentric and non-eccentric waveform. So you need some way to model the new physics that you're looking for. And if you really have no idea, then you can choose something that's model agnostic, but it's not going to tell you a lot about the astrophysical implications.
Right. So for example, like if you, for some of these, for example, for GW 190521, that there are like different interpretation, like not the standard interpretation from the collaboration, like how. So some of them, like they evaluated like the Bayes factor, and it's like comparable to the one of the quasi-circular binary black holes. So how can you understand which interpretation makes more sense or not?
Yeah. If the Bayes factor between the two models is not like particularly statistically significant, then it's really hard to say. Everyone has kind of their own implicit prior odds for different scenarios. And so if one person's really excited about Prakastar mergers, then their personal prior odds for that might be higher. But yeah, so I guess, you need a strong Bayes factor in order to be able to make a confident statistical statement. But barring that, I guess it is hard to say one is definitely right compared to the other.
So, but if someone like choose a different model with different priors, and you get a very higher Bayes factor, in that case, this is a good indication, or?
Yeah, that would be a good indication that one model is a much better fit to the data.
Okay, thanks.
Yeah.
Okay.
Yeah.
Yeah.
Oh, go ahead.
More questions.
No. Related to this, Sylvia, you mentioned that a good Bayes factor is 3000. Is that related to a specific statistics or is heuristic value?
I think it's something like 5 sigma, but it is kind of just tradition. Like that's what has been used in the past, and so that's what's typically accepted.
But is there a statistic for the Bayes factor? I don't remember if it follows a specific distribution.
So the distribution will depend on like your noise properties and the hypotheses that you're considering. I don't think there's one specific distribution that will apply in all situations.
You mentioned 5 sigma, right? Well, anyway.
Yeah, and I guess just quickly, this is the result of our short little sampling problem with Bilby. We have posterior samples for the chirp mass, the mass ratio, the time, and the phase. So this is pretty easy to set up. If you want to play around with it, I can circulate this notebook, since I guess I'm not sure if you'll have access to the chat there.
Yeah, there's another question.
Yeah, this question is more related to the sine wavelet reconstruction, because as you said, with this kind of reconstruction, it's good because we don't have to think about if it was a compact coalescence or an exotic compact object. But you said that we can only get the reconstructed waveform. I mean, we don't have an access to the astrophysical information. But maybe, I mean, if this means also that we can get the spectra of the signal. So maybe, I mean, is there a way to get some information, like, for example, with the spectra, we can get the modes that have been excited during the signal. So maybe is there a way to get indirect information about the astrophysical properties only with the sine wavelet reconstruction?
Sure. So if you have a way to map between sine Gaussian and whatever other model you want to consider, you can just compare kind of, if you don't want to do it rigorously, you can kind of eyeball it and get constraints that way. But if you already have that other model, the best thing to do would just be to use that directly in your likelihood, because then that would allow you to obtain estimates for the parameters of that model rather than some generic shape of the signal that you would then have to compare to that model as a second step.
Okay, any other question? If not, let's thank Sylvia again.